Welcome to Brain Vision.
The expression the problem is asking us in the first item is precisely the expression that results from applying Newton's second law to this situation. So in order to do that, let us choose our reference frame. I will be using this one, a vertical axis that I will call a y-axis and a horizontal axis that I will call the x-axis. This is my reference frame. Now let me apply Newton's second law in this reference frame. So by doing that on the x-axis, and I'm applying Newton's second law to the ball that is hanging, we get that the net force on the x direction in that ball is equals to the mass of the ball times its acceleration in the x direction. First, notice that the acceleration of the ball in the x direction is equals to the acceleration of the van in that direction. So let me call it A. Then the net force in the x direction is equals to the mass of the ball times A. But the net force in the x direction is composed by only one force, which is a component of the tension force. We can decompose the tension force as follows. We can do a horizontal component, which is the x component, and the vertical component, which is the y component. Then we can write this equation as the tension component x is equals to the mass of the ball times the van acceleration. Now we can relate the x component of the tension with the magnitude of the tension and the angle theta. To do that, we have to use a triangle that is formed by the tension and its components, and the triangle is the following. We have the tension pointing in this direction, we have the y component, and we have the x component. They form a rectangle triangle where the hypotenuse is the tension, this side is the y component, and this side is the x component. Notice by the geometry of the problem that the angle between the tension and the direction of the y component is theta. Then this angle of the triangle is theta. Then the relation between the tension, the x component, and theta is given by the sine of theta, because Tx is the opposite side of the triangle to the angle theta. Then the sine of theta is given by the opposite side, Tx, divided by the hypotenuse t. Then Tx is equals to t times the sine of theta. So t times the sine of theta is equals to the mass of the ball times the acceleration of the van. Still, there is no gravity appearing in this expression. How can we make gravity appear in this expression? We have to use Newton's second law in the other axis to calculate a relation between the magnitude of the tension and the magnitude of the weight force. Before doing that, let me erase the board. Okay, it goes as follows. By doing the same analysis for the y-axis, we have that the net force in the y direction is equals to the mass of the ball times its acceleration in the y direction. Note that the ball is standing in this position, so it's not moving on the y direction and it's not going to move. So its acceleration in that direction is equals to 0. Then the net force that acts on the ball in the x direction is 0. But this net force is composed by two forces, the y component of the tension and the weight force. Then the y component of the tension minus the weight force is equals to 0. So the y component of the tension is equals to the weight force. Now we have to go back to that triangle formed by the tension and its components to determine what is the relation between the y component of the tension and the magnitude of the tension. Remember, the triangle was as follows. This was the y component, this the x, this is the magnitude, and this was theta. And this is a 90-degree angle. Then, as we want a relation with ty, we have to use the cosine of theta. So the cosine of theta is given by the adjacent side ty divided by the hypotenuse t. Then ty is equals to t times the cosine of theta. So t times the cosine of theta is equal to the weight force, which is the mass of the ball, times the acceleration of gravity. Then, the magnitude of the tension force is given by the mass of the ball times the acceleration of gravity divided by the cosine of theta. Then we can plug in this equation into this tension to get the following. M times G times the sine of theta, this is divided by the cosine of theta, is equal to the mass of the ball times the acceleration of the van. We have the mass of the ball on both sides of this equation, so we can simplify it. And also notice that we have a sine divided by a cosine, and this is a tangent. Then we end up with the acceleration of gravity times the tangent of theta being equals to the acceleration of the van. And this is the final relation the first item is asking us. For the next item, we have to clear the board here, so let me do that. And now, for the next item, we have to suppose that theta is equal to 10 degrees and calculate the value of the acceleration. So now theta is equal to 10 degrees. What is the acceleration? We can use this expression. The acceleration is equal to g. Remember that g is approximately 9.8 meters per second squared times the tangent of 10 degrees. This results in an acceleration of approximately 1.73 meters per second squared. Then we also have to answer the last item, which asks what is the angle theta when the van moves with a constant velocity. So as the van is moving with a constant velocity, its acceleration is equal to 0. Then g times the tangent of theta is equals to 0. We can send g to the other side, so the tangent of theta is equals to 0. And then, when the tension is equals to 0, we can conclude that it's because the sine is equals to 0. And the angles that have the sine equals to 0 are 0 degrees and 180 degrees. But notice that in this situation, it's impossible to have this 180. So our answer is that theta is equals to 0 degrees.